Alright, grade 12 chemistry, let's do some math. Today we're going to be doing a lot of our mathematical foundations for equilibrium. In particular, we're going to learn about using ice tables. We're going to take a little detour into vapor pressures. And we'll talk about solubility, equilibrium, and we'll do some solubility practice problems using some of this algebra that we're going to be examining today. So jumping into it, this is what's called an ice table, and ICE stands for initial change equilibrium. That's what it stands for. It's used to make algebra, so it's used to make a mathematical expression, an algebraic expression, and it'll help us predict the changes in equilibria when we have an equilibrium shift. So here's an example. We've got HCN making H plus and Cn minus. All of them are aqueous, so all of them are going to be part of our equilibrium. If I started with a concentration of HCN of 0.15 moles per liter, here's how I set up my table. You write initial change in equilibrium. You write in the initial, here's the initial, right? I start with 0.15 moles per liter. So I've got 0.15 moles per liter of this stuff, nothing here, nothing here. So 0, 0, 15, that's my start. Now my change, I know this is going to push to the right because there's none of this to start, and it's got to push to the right. It's the only way it can go. So it pushes to the right, which means this is going to lose a certain amount of concentration. And assuming a constant volume, that's going to lose, we say it loses X concentration. If it loses that many moles in whatever container it's in, this side is going to gain that many moles, and it's in the same container. So whatever concentration this loses, that's the concentration this is going to gain, because it's one of these for every one of these. So this loses one, this one gains one. If it was like two of these, it'd be 2x, and three of these would be 3x, and so on. That's how it works. One side loses, one side gains, so it's a minus on one side and a plus on the other. So you kind of have like this dividing line where everything on this side is going to lose, everything on this side is going to gain in this specific case. But yeah, it's opposite. And then the last thing, the equilibrium, is you add these together. You add these two columns together. You've got the initial and you've got how much it changed by. So at equilibrium, you're going to have 0.15 minus x. Here it's 0 plus x, which is where x comes from. This is 0 plus x, which is where x comes from. So that's how you set up one of these tables. And this helps us make a mathematical expression. We have this mathematical expression for what's going to happen at equilibrium. So once we've set it up, this bottom part is what we really care about. So I'm just going to highlight that, right? This is what we care about. This is our concentration at equilibrium. And it helps us solve. One of the easy ways that we could solve this is if we have some kind of test, for example, that can test for the concentration of one of these, maybe this H+, we could do a pH. We could figure out what the acidity is, and that's our H+. Right, and let's say that this gives us an H+ value of 0.10 moles per liter. 0.10 mole per liter. Right, that tells me that X is equal to 0.10 moles per liter, because I know that at equilibrium, that my concentration of H plus is X. And if the concentration of H plus is found to be 0.1, then X is 0.1, which means this side here is also going to be 0.1, right? I didn't measure the concentration of cyanide, but using my math, I know that it's the same, because it was also 0 plus X, and this is 0 plus X. So the same expression, same value, 0.10 mole per liter. So I can figure out the concentration of a different species in the reaction based on the concentration of this one. And I can also figure out this guy, 0.15 minus X. Right, minus X, and we know what X is. X is 0.10, 0.10. So therefore, the concentration of HCN at equilibrium is going to be 0.05 mole per liter. So that's how you use an ICE table. It's this gives you the algebra, and then you have to use a different piece of information to figure out what your equilibrium concentrations are. So that's one cool way to do it, but it requires us to actually test. There's an even cooler thing we can do with this, and that is if we have the K, if we have the equilibrium constant, we can actually use the ICE table to predict what X is going to be. And then if you know X, you know all the rest of them. So same setup, we have 0.15 of this to start, minus X, so 0.15 minus X, plus X, so plus X, plus X, plus X. That just comes from the equation. And I've actually looked up the Kc. This is the real K of this reaction, 6.2 times 10 to the negative 10. It's a very small K. And I want to predict the equilibrium concentrations. So here's how this shakes out. We have to write down an expression for K. So here's our reaction up here. We just did this in the previous video, so if you're confused about what I'm about to do, K, the concentration K, is going to be the H plus, the Cn minus, right, products over reactants, over the HCN. Right. But we know two things. We know what K is. We actually know the value of K. Right? We know the value of K. We know that number there is 6.2 times 10 to the negative 10. And we know this algebraic expression, right? That we know that this is X, and that that's X, and that that's 0.15 minus X. So we can rewrite this as 6.2 times 10 to the minus 10 is equal to X, because that's my concentration of H, right? That is X times X over this one, right? The concentration of HCN, 0.15 minus X. So 0.15 minus X, 15 minus X. Right? And what we're going to get here is actually a quadratic, which is kind of cool. Right? X times X is X squared. 0.15 minus X has to be 0.15 minus X. But one thing that we can do here, well, I'll show you that. I'll write it out first. So 6.2 times 10 to the negative 10 equals, it's going to be X squared because it's X times X over 0.15 minus X. Right, so that's our expression that we have to solve. And it is a quadratic. If you take the 0.15, you can multiply the 6.2 times 10 to the negative 10 by the 0.15 minus X and get a quadratic expression. And you can solve it using the quadratic formula if you want. But there's a shortcut we can take, a practical shortcut, because chemistry is a very practical science. And that's thinking about what this means. 6.2 times 10 to the minus 10 means that the reactant is heavily, heavily, heavily favored. You know, to the tune of 1 in 10,000, something like that, because it's 10 to the minus 10. So that means that X is going to be exceedingly small. Right? If this is such a small number, X is going to be very small. So we can do like the calculus thing, where we just kind of take away that minus X. So what we can do, one method of solving it, if the K value is very small, you have this method of solving it where we can take the bottom and just say that that's like this 0.15. We can say it's going to be pretty close to just 0.15 because it's 0.15 minus a very small number is basically what I'm getting at. So that turns it into 6.2 times 10 to the negative 10 equals X squared divided by 0.15. And then to rearrange, X squared is going to be 0.15 times, right, we multiply by 0.5 on both sides, times the 6.2 times 10 to the 10 to the negative 10. Right, rearrange like that, and then x is just going to be the square root of that, whatever that's going to be. What is 0.15 times 6.2 times 10 to the negative 10? 6.2 times 10 to the negative 10, 9.3 times 10 to the negative 11. Square root of 9.3 times 10 to the negative 11. And then x is going to equal we're going to square root that, something very, very small. It is 1, 2, 3, 4, 5, 6, 9.6 times 10 to the negative 6. Moles per liter. Right, 9.6 times 10 to the negative 6 moles per liter. So there's a tiny bit of the hydrogen. So that's X, right? That's the hydrogen and the cyanide. They're very small. And just as predicted, X is very small, so that basically doesn't touch the 0.15. It's a rounding error at that point. You know, it's 0.0000096. That's a very small number. So that's one way to do it if you have a very small k. If you have a very big k, if you have a k that's big enough, you're going to have to use the quadratic formula here, which I'm just going to pause and I'm going to write it out so you don't have to watch me write math using my mouse. So I'm going to pause and write it out just a second. There we go. I wrote it out as an actual quadratic. So what I did was I took the 0.15 minus x and I multiplied it through. Like I multiplied the 6.2 times 10 to the negative 10 by both of these. So this is 6.2 times 10 to the negative 10 times 0.15. And then the x, the minus x, so this times minus x gave me minus 6.2 times 10 to the negative 10 x. That's equal to x squared on the other side. Rearrange it to standard form. And then you can use your quadratic equation, you know, x equals this minus b plus or minus the square root of b squared minus 4ac all over 2a. With a equals 1, b equals minus 6.2 times 10 to the 10, negative 10, and c is 9.3 times 10 to the negative 11. You just run it through the quadratic equation. I'm going to do that with an online solver because I feel lazy. So I just realized that I made a math fail. When I brought these to the other side, this should have become a plus. The minus 6.2 times 10 to the negative 10, that should have become a plus. Right, when I brought that to the other side, it becomes a plus, and then this one should have become a minus. So you can tell it's been a while since I've done a quadratic. But when we go to the equation solver, here we go. That's 6.2 times 10 to the negative 10, and this is minus 9.3 times 10 to the negative 11. And I get my roots as 0.000009643. Meanwhile, my answer before was 9644. So it's the same, right? It's the same. Right? It's still 9.6 times 10 to the negative 6. If we include the quadratic or not. So our shortcut worked. Our shortcut's okay. Yeah, so that's using an ice table to solve these things, and going to using the k value and the ice table to predict equilibrium concentrations. I'm not going to actually make you guys do this. I just want to show you that it's possible because it's something that you'll be doing in university if you take chemistry in university. We will do it in a sort of way. We're going to do it for acids and bases, but a lot of the time we'll be able to use our shortcut, our simplifying shortcut. We'll use the blue method instead of the red method over here. Okay, that's that. Let's get into vapor pressures. Okay, so vapor pressures are really cool. This is why hot air can hold more water. You might have heard that in different science classes. I think I use it with like my grade 10 science class because explaining equilibrium would be too annoying. But here's the real reason that hot air can hold more water. Here's the reason why dew happens. This is why water boils. This is why anything boils. It's an equilibrium. You've got an equilibrium between the liquid and the gas, and this diagram is trying to show what's happening. Basically, there's molecules that are coming in and hitting the liquid and turning into liquid. and dumping their energy into the liquid, and then there's molecules in the liquid that have a lot of energy and they're flying off at the surface and turning into a gas. And there's an equilibrium. There's a inwards process and an outwards process. There's an equilibrium here. But the cool thing about this equilibrium, we can set it up, is that the expression of K or Q is very, very simple. Because on the left side, you've always just got a liquid or a solid. On the right side, you've got a single gas. It's always a single gas on one side and a single liquid on the other. And so the expression is always exactly the same. It's literally just, for the water, for example, for the water, it's just going to be H2O, right? It's just going to be the concentration of H2O, right? K equals just the concentration of H2O. For the ammonia, it's literally just going to be the concentration of ammonia. Right, the gas phase, I guess. Right, and the gas phase of ammonia. So it's always the same. The vapor pressure is just the moles per liter concentration of the gas. Now the gas, right, the gas, that's interesting. Because if a container has a certain volume, only a certain number of moles of the gas are going to be in vapor form at any time. So you have a closed container, though at a certain temperature, there will be a known quantity of water vapor, water molecules in gas form up there in the gas because of this this equilibrium where it transits between the phases. It's in moles per liter, but it's easier to measure the pressures of gas. So usually we use this as a pressure constant, which is instead of Kc, which is concentration, you'll see Kp, which is pressure. Kp is pressure. So gases have both. Gases have a Kc and a Kp. When you have a gas and an aqueous solution that are doing something, then you'll be using the concentration one. If it's just a pure gas equilibrium like this, pressure is easier to talk about because we can do more things with air pressure. More meaningful to talk about air pressure than it is to talk about concentration. We use the gas law to prove that that this works. Basically, PV equals nRT. If you rearrange it for pressure, so this PV equals nRT, the ideal gas law, P becomes nRT over V. We're dividing by V. But what I'm going to do is I'm just going to divide the N by V because I'm allowed to do that. N over V RT, and N over V is moles per liter, right? N over V, moles per liter. That's concentration. So the concentration is part of this, and then R is a constant, 8.315, right? It's the gas constant, the ideal gas constant. And T is the temperature in Kelvin. And so the pressure will go up with the temperature in Kelvin. Also, the value of K goes up here with the temperature because it's an endothermic process. Turning into a gas is endothermic. So increasing the temperature also pushes K further towards the gas. So it's increasing the K, and it's also increasing just the raw pressure of those moles because they're moving faster. And so you get this curve of, this is the vapor pressure of water based on temperature in degrees Celsius, vapor pressure in kPa. The atmosphere at sea level is 101 kPa, and you see that at 100 degrees Celsius, this is hitting 100 kPa. Hitting 100 kPa. Okay. And at that point, the vapor pressure of the water is equal to the outside pressure. And hey, guess what happens? It boils. Wow. Vapor pressure increases with temperature. And so this saturated vapor, if you have this and it's saturated with the vapor, and you cool it down very quickly, not even that quickly, it'll condense from that invisible gas phase water vapor. There's water vapor in this room right now. There's probably like 50% humidity in this room, so I know that there's water vapor in here. When it condenses down, suddenly it turns into little droplets of water, and those scatter the light, and so it becomes a cloud, or mist, or fog. So that's how clouds form. That's how fog and mist forms. Basically, the air has to be holding a bunch of water and then cool down below the vapor temperature below this condensation point, which is an equilibrium thing based on the temperature, because K changes with temperature based on this curve. This is why clouds tend to form at the same altitude. If you ever looked out on a cloudy day, all the clouds, the bottoms of the clouds are all one single altitude. That's because that's where the temperature drops below the dew point. That's where the temperature drops below the saturation vapor pressure of the water. And now the equilibrium will push the water out of gas phase and into the liquid phase, where it makes tiny droplets and scatters the light, and that's what happens in a cloud. And the opposite is boiling. The opposite is boiling. If the vapor pressure is above the ambient pressure, the water wants to make more pressure than there is outside, and so it'll boil. It'll boil. If you've got an open container and the air is not saturated with water yet, you've got this Le Chatelier's kind of principle going on, where the water turns into gas and the gas disperses, so the pressure never increases. And that's why water will evaporate, and it will evaporate faster when it's hotter. That's why the air can hold more water when it's hot, because there's a higher vapor pressure. And there's a lot you can talk about here. This is how pressure cookers work. Pressure cookers, this curve in terms of pressure versus temperature, if you keep increasing the pressure, if you trap the pressure and keep increasing the temperature, then the boiling point of the water gets higher and higher and higher and higher. So you can cook food much faster because the water is higher than 100 degrees Celsius. It's boiling at much, much, much higher than 100 degrees Celsius, and things like that. You can also boil water at very low temperatures if the outside pressure is low. It's hard to cook on a mountain because water boils at much lower temperatures. For an extreme example of this, I'm going to link this video down below. It's a vacuum chamber, and this is water. This is a thermometer here. It's at 24 degrees Celsius. And as the air comes out of the vacuum chamber, you'll see the water start to boil at 24 degrees Celsius. Right? A very low pressure on the outside, so the vapor pressure of the water at that 24 degrees Celsius is enough to make it boil. And the really cool thing is, because boiling is endothermic, it actually cools down as it boils. That temperature actually drops. So, you can actually see the temperature dropping in the thermometer over time. It's at 15 degrees Celsius and so on. So I'm going to link that in the description. Check that video out. It's super duper cool example of a vapor pressure equilibrium. Hey, we're done with vapor pressure. So now you know how clouds work, you know why hot air holds more water, you know how your pressure cooker works, all kinds of cool stuff like that. So that's done. Let's talk about solubility. Solubility. Solubility, a little review from grade 11 chemistry. Usually we use grams per 100 mils to talk about solubility. Like salt is like 35, I forget how many grams per 100 mils it is for salt, but quite a lot of salt can get into 100 mils of solution. Sugar is even better. At certain temperatures, you can get more than 100 grams of sugar into 100 mils of solution. You're basically making syrup. That's one way to do it, but there's a problem chemically there because different molecules have different molecular masses. So like sugar weighs a lot. A molecule of sugar weighs 180 grams per mole versus salt, which is like 58 grams per mole. It throws stuff off when you've got this mass issue. So grams are not great. We like moles. So molar solubility, moles of solute per liter of solution is better. It's a bit more universal. Solubility in moles per liter. But even better is using an equilibrium, because solubility is also an equilibrium. You can think of it a lot like a vapor pressure equilibrium, like this kind of thing going on. This is a liquid and a gas, right? A liquid and a gas, but think of it as a solid and then the ions off in the water. Imagine that this is water and it's pulling the ions apart. Same idea. You can have ions coming in and becoming part of the crystal, and you can have the crystal releasing ions. The water can come in and grab the ions. If you think way back to Unit 1, we had that video where water was pulling apart the salt crystal. Well, the salt can come back on to the crystal as well, because the positives and negatives are still are still in play and stuff. So this kind of thing also works for a solubility equilibrium. Here's a solubility equilibrium. You have a solid and two aqueous solutions. So solids don't factor in. So it's just going to be the aqueous solutions, and there's a K value here. Right? You can actually figure it out. There's a concentration K. It's specifically a concentration K. Right? It's not a pressure K. It's kind of meaningless to talk about pressure of an ion. So it's an equilibrium thing, and so this is where we get KSP. KSP is the solubility product constant. KSP, solubility product. Solubility product constant, because it's always a product, right? It's always a multiplier, because this is going to fall apart. Every compound, ionic compound, is going to fall apart, and it's going to create ions, and those we just multiply the ions together, right? So K here is going to be, right, we ignore the NaCl, but it's products over reactants. And the products is the sodium multiplied by the chlorine, right? The concentration of sodium multiplied by the concentration of chlorine. That is that, and that's KSP, I guess SP. And we should probably throw the state symbols in there just to be good chemists. State symbols. There we go. So that's how you calculate it for KSP. It's independent of volume. It's independent of molar mass. It's independent of a lot of things. It's just a K value. It's an equilibrium. At a certain temperature, this will always be the solubility, right? The maximum amount of solubility. Because if you have more than this happening, you'll end up with solid forming. We like it. You do have to watch out for it though, because of this kind of thing. If it's, say, calcium chloride, when calcium chloride dissolves, you get one calcium and two chlorines, right? One calcium and two chlorines. And so the KSP is, there's a 2 here now, so that's going to square your chloride term, right? It's going to square your chloride term. And even more interestingly, like if 3 moles per liter, right, dissolve, right, if 3 moles per liter dissolve, for example, then the concentration of Ca is going to be 3 mole per liter. But the concentration of Cl minus, because there's 2 of them that dissolve, right, there's 2 of these that dissolve for every 1 calcium, is going to be 6 moles per liter. Right, we have to watch out. For that as well, because of that 2, that sneaky little 2. It not only does it make a square here, this concentration is actually twice as big as this concentration as well, because of how it works. So that's KSP. There's also a QSP. QSP. It's called the ion product. And it helps us, just like Q and K helps us in reactions. QSP and KSP help us figure out if a solution is saturated, unsaturated, or supersaturated. Remember that at equilibrium, the rate of solid and aqueous is the same. If we're below equilibrium, if Q is less than the equilibrium, then it's likely that the solid will make ions. If Q is greater than the equilibrium, too many products, then the products are going to turn into a solid, and you'll get a precipitate. You'll get a reaction, a precipitation reaction. So we can use it to figure out if a precipitating form. It leads to the common ion effect, where we can add common ions, and that changes the solubility of a substance. We'll talk about that when we get to these practice problems, which is what we are about to do. So let's do some solubility practice problems. I'm going to pause and get that set up. Okay, we're going to start with our first one here. It says that the molar solubility of MgF2, magnesium fluoride, is 2.7 times 10 to the negative 3 moles per liter. That means that at maximum, 2.7 times 10 to the negative 3 moles per liter of magnesium fluoride will dissolve in our water. We have to determine the KSP at whatever that temperature is. So we've got, let's make an expression for this. It's MgF2 and we're going to have I'm going to be lazy and do the equilibrium sign like that. We have to think about how this thing is going to dissociate. How is it going to dissociate? Well, it's going to be 1 magnesium, and we're going to get 2 fluorines because it's MgF2. Right, 1 magnesium, which is a 2+, and 2 fluorines. Right, 2 fluorines. I'm going to put that in red just to highlight that there's 2. So if there were 2.7 times 10 to the negative 3 moles per liter of MgF2, right, and if all of that dissolved, then the concentration of Mg, 2+, is going to be, well, that 2.7 times 10 to the negative 3, because it's just one of those comes off of each one of those, 2.7 times 10 to the negative 3. But the concentration of fluorine, is twice that, because for every 1 magnesium, I got 2 fluorines, right? I got 2 fluorines for every 1 magnesium. So double the 2.7, it's 5.4 times 10 to the negative 3, because that's what the, 2 times that is. Now we have to put that into our KSP, right? Our KSP expression is going to be the concentration of magnesium, 2+, right? The concentration of magnesium times the concentration of fluorine minus squared. Right, and it's squared because of that 2, right? Because of that 2, it's squared. So that's going to equal. It's going to equal Mg 2+. Oh, there's going to, well, let's actually put the numbers in. 2.7 times 10 to the negative 3 times 5.4, right? That's the fluorine that we just figured out, negative 3, and that's squared. Right, that one squared, but only that one. It's not both of them squared, just that one squared. And so I'll put that in my calculator. Let's get that going. 2.7 times 10 to the negative 3 times 10 to the negative 3 times 5.4 times 10 to the negative 3 squared. That's very, very, very small. 7.8 times 10 to the negative 8, or 7.9 times 10 to the negative 8. 7.9 times 10 to the negative 8. That's the answer. I remember that KSP doesn't have any units. No units in a KSP value. So yeah, 7.9 times 10 to the negative 8 is the KSP of this MgF2. So you have to kind of watch out for these things. Now, going the other way, going for molar solubility, is you have your KSP, you want to figure out how many moles per liter. Well, same thing, you start with the formula, BaSO4. This one is going to decompose just straight up. It's right, it's going to decompose just like that. And so it's just going. This is just going to be. We're going to give it a value. We're going to stick a variable on there. That's going to be x, and that's going to be x. I should probably change those colors. Let me just change those colors real quick. Make it red. Right, x and x. We'll set that to x, and that must have come off of this guy, right? If that's x and that's x, this must be x as well. Because it's 1 to 1 to 1. So that's it's almost like an ice table, right? This might be minus x if it goes down. This is plus x. And this is plus x. And so we know then that the concentration is going to be, right? In this case, x times x, right? And that's the KSP, 1.5 times 10 to the negative 9. X times x is 1.5 times 10 to the negative 9, which means that x squared is 1.5 times 10 to the negative 9. And so x is the square root of that number. So square root of 1.5 times 10 to the negative 9. Ooh, something went weird there. Negative 9. There we go. 3.9 times 10 to the negative 5. 3.9 times 10 to the negative 5. And that's in moles per liter, right? There's the little square brackets. So this actually does have a unit. It's moles per liter. Oh, that's big. I should make that small. Yeah, so that's how you go the other way. You have to assign these x's and figure out what that means. This can get a little bit interesting when we have something like this, right? FeOH3, and it's got this tiny KSP. We have to do the same thing. FeOH3, right? FeOH3, and that's equal to Fe, just Fe plus, and it's an Fe3 plus. I'm not going to put the charges in just because we're hurting on time right now. Plus OH, but there's 3 of those. There's 3 OHs because there's a 3 there. Right? Every time one of these dissociates, we get 3 of these OHs. And so when we put that through our equilibrium, our ice table, right? If this goes down by x, this would go up by x. This would go up by x, and this would go up by 3x, and that's really important that this goes up by 3x, because when we do our KSP, right, our KSP, it's going to be Fe, concentration of Fe, and the concentration of OH cubed, right, cubed, because of that 3, cubed. And then you can put in the numbers. 6.0 times 10 to the negative 38 is equal to, and we'll put that up, 10 to the negative 38 is equal to x, right, that's the x for Fe, and the OH is 3x, but that 3x is cubed, 3x cubed. So when that cubed applies to the 3 and the x because it's inside the brackets. Right? Exponent rules. Hey, you thought you could get away from that in math, huh? But nope, they're still around. So this guy sticks around, like we're keeping the same. 6.0 times the negative 38 is equal to x stays. Then the 3x cubed, right? The 3x cubed, the cubed applies to the 3 and to the x. So 3 cubed is 27. 3 times 3 times 3, and then x cubed. Right, we'll bring that exponent into the brackets. And then so we get then 6.0 times 10 to the negative 38, that thing, is equal to 27x to the 4. 27x to the 4. Right, and then from there, what you'll end up with is, we have to solve this expression. First, we're going to divide by 27. Right, so I'm just going to paste that. That over 27. 27 is equal to x4. X to the 4. That over 27 is equal to x to the 4. So let's divide that by 27. 6 times 10 to the negative 38 divided by 27. 2.2 times 10 to the negative 39. I'm not even going to try to write that. 2.2 times 10 to the negative 39 equals x to the 4. Right? And so then this number, to get x, it's going to be x is going to be the root 4 of that number, the fourth root. In your calculator, you could also just, you can cheat. Not cheat, you can be smart about it. And just go to the power of 1/4. Right, just take it to the power of 1/4. Right, it's root 4. So let's do that. 2.22 to the power of brackets, always brackets. You can do 0.25 if you want, or just 1/4. I get 2.1 times 10 to the 10. 2.17 times 10 to the 10. To the negative 10 equals x, right? 2.17 times 10 to the negative 10 equals x, right? And then we can compare that up here, right? 2.1 times 10 to the negative 10 equals x. I just grabbed that and brought it up. Let me just, for posterity's sake. So then the concentration of Fe at equilibrium is 2.17 times 10 to the negative 10. And the concentration of OH is 3 times that. It's equal to 3x, which is equal to 2.17 times 3, 6.51, 51 times 10 to the negative 10. Oh, and that's in moles per liter. So let's do a unit. So I expect you guys to be able to do these kinds of calculations on the test to figure out the moles per liter concentration at equilibrium of these things, right? The molar solubility of these. Oh, and obviously the FeOH3s, the molar solubility is going to be 2.17 times 10 to the negative 10. That's a long enough lesson. There's some more problems here. These are common ion problems, but we're going to save that for class. So yeah, thanks for paying attention to this long one. I know there's a lot of math in this, but it's important math. It's going to really help you guys out in university if you take this stuff in university. So yeah, thanks for paying attention, and I'll see you in class.